what I want to do today is I want to finish up naming from the concept and construct of, we spent a lot of time doing ionic nomenclature, naming of ions. I want to get into the other forms of naming, and that is the naming of acids and the naming of covalent compounds. Because if we can understand the three constructs in terms of how they're put together, then really all that naming becomes for us is a matter of recognition. Okay, do I have an acid, or do I have a covalent compound, or do I have an ionic compound? If I can recognize that, then I can go into one of three lanes of nomenclature. So to finish up Ionic, we're going to talk about ions, in particular the anions. Remember, anions have a negative charge. And they come in two different forms. They can either be non-metallic monoatomic ions, like your sulfur ion, your sulfide, your oxide, your selenide, your halogenide, so halides like fluoride and chloride, bromide, or they're polyatomic anions, things like carbonate, oxalate, nitrate, nitrite. So we pointed this out in a previous lecture. It's worth repeating. If they are non-metallic anions, so the ones that are not polyatomic, all that we do is we fix their endings by changing them to IDE endings. And so that IDE ending is a very telltale sign, because if you see an IDE ending like that, that should immediately spring into your head, oh, this is monatomic. I just need to find the element that goes with it. So if I get oxide, I know it's an element with a negative charge. Oxygen, oxide. If it doesn't end in IDE, then we've got other things to consider. That's when we have to start looking into that prefixing system, that suffixing system, and so on. When we name ionic compounds, it always follows the same structure. We name the cation, then the name of the anion. So if I look at MgCl2, the name of my cation, Mg is the magnesium ion, Cl would be the chloride ion. Put those two together, and I get magnesium chloride. All I do is smash together the two names, pick off the word ion from each of them. For K2S, I've got the potassium ion from the K. I've got the sulfide ion from the S. Put them together, take off the ions, I get potassium sulfide. So it's a matter of recognition. We're either recognizing elemental ions, monatomic ions, and those are just by name of elements. If it's negatively charged, if it's non-metal, we fix the ending to IDE. Otherwise, it holds exactly the same. And then I just put the two names together. And this would be the case if I had polyatomic ions as well. The only difference would be instead of sulfide, I would have to recognize the polyatomic ion that was attached to it, whether it was sulfate or carbonate, oxalate, whatever the case may be. But the anion will always be second. It's always going to follow that formula, cation, then anion. And so if I put in polyatomic ions, again, it's still a matter of recognition. I recognize NH4 is my cation here. That's the ammonium ion. Cl, chlorine, fix the ending, so it's chloride. And then I put the two ion names together. Ammonium chloride is the end result. This works on the other direction as well. Here's a little bit of a tougher one where now we've got iron. Iron has a variable charge. It's a transition metal. And so we have to recognize the type of iron. Here's where our context clues are going to come in. So we can almost think of this as a reverse crisscross. The subscript tells us the identity of the ion. So the 3 here on the hydroxide mean that we had a 3 positive charge on the iron. The 1 on the iron means we had a -1 charge on the hydroxide. And we know from our polyatomic ion list that hydroxide is -1, so that does make sense. We have to identify iron by its charge, so that's where the iron 3 comes from. OH is hydroxide. We get iron 3 hydroxide as a result. So when we're identifying compounds by their formulas, and we know that a variable charge is present, so we know that we have a transition metal, and it's not one of the transition metals that is constant. So it's not your zinc or your silver or your cadmium. In that case, we can use that reverse crisscross, turn the subscripts, flip them over to find the charges to help us identify the proper charge on that ionic compound. So let's do some more examples here. So in the first one, recognize that it's ionic. I've got a metal and a non-metal. I'm going to split it. Na is sodium. Cl is chlorine, which we're going to fix to chloride. So NaCl becomes sodium chloride. MgNO3 taken twice. Again, recognize that we've got a metal there. The metal is going to be our split between cation and anion. Magnesium is Mg. NO3, that comes from recognition over time. NO3 ion is the nitrate ion. So this is magnesium nitrate. With regard to that 2 there, why is that 2 there? Why do I need 2 nitrates to every 1 magnesium? David? It does. The charge on the magnesium side is positive 2. Nitrate only has a negative 1 charge, so I need 2 of them to balance out the charge. Does that mean I turn this into dinitrate? No. Subscripts on ionic compounds never get turned into prefixes. If there is a prefix on an ionic compound, that's because that is the name of that particular ion. So for example, dichromate. Dichromate ion is not 2 chromate ions together. It's its own ion. Cr2O7 minus 2. 2 chromates would actually be Cr2O8. So it's not the same. Okay, once again, barium and oxygen. So I've got a metal and a non-metal. Split the anion from the cation. Ba is barium. O is oxygen. Fix the ending. Oxygen becomes oxide. Barium oxide is the name of this compound. Last one, lithium and nitrogen. Lithium is a metal, nitrogen is a non-metal. So I split it there. Lithium is the name of the cation. The nitrogen is the anion. Fix the ending to IDE. Lithium nitride is the product. And again, the subscript here is all about charge differential. Nitrogen is a -3 ion. Lithium is a +1 ion. I need 3 lithiums to balance out the nitride. All right, any questions here? Adrian.
How did you get nitrate again on number 2?
So nitrate, that's a recognition thing. I have to recognize that that cluster of atoms, NO3, represents a polyatomic ion, the nitrate ion. So polyatomic ions is just recognition of clusters of atoms together. They always follow the same pattern. So for example, nitrate ion, NO3 minus 1, NO2 minus 1, this was nitrate. This one down here with 1 fewer oxygen, all I do is change that ATE ending to an ITE ending because of the 1 fewer oxygen. Charge doesn't change. The only thing that changes in those ATE and ITE ions are the number of oxygens. And ATE will always be 1 more than ITE. So it's just a matter of recognition. And that, the best way to do that is flashcards or some other kind of memorization technique where you're just kind of going through it again and again and again and again. Once you kind of get used to it, you do see that there are patterns that emerge, but you have to have a foundational base in order to use those patterns. All right, let's look at this one. Answer with me together. If you're on Zoom, type in the letter of the correct answer into the chat. Ba3P2. What is the name of this compound? right, we've got a couple of answers in the chat. What about the several of you that are here? What you're thinking? C? Okay. Someone explain why is C the correct answer? Okay. So that's one thing that we could look at. If we're reversing our crisscross, then we would recognize that the phosphide has a -3 charge and the barium has a +2 charge. So from that, we could eliminate B and D because they have the wrong charge for the barium. So now we're between these two. First of all, is barium in a position where it needs to have a Roman numeral? Look at the periodic table. Where is barium? Barium's an alkaline earth metal. Transition metals are the only ones that we would have to put Roman numerals on. Roman numerals are only used if there are multiple charges. If you are using a Roman numeral, that implies that there is another version of this ion out there. So that's the first problem. The second problem, if I've got an ion that ends in ATE or ITE, it's got to have oxygen in it. This one doesn't. The IDE ending implies a monatomic ion, which this one obviously is. P is by itself. It's not PO something, it's just P. So C is the correct answer. All right, let's look at another one here. Same deal. If you're zooming in, give me a correct answer in the chat. Those of you here, think about it for a second and go from there. This one's a little tougher. You have to know your polyatomic ions. Now, I'll give you a hint. We've got our dividers right here, cobalt and SO4. So that's our first hint that we can look at. One hint I can tell you, there's not a single ITE polyatomic ion with 4 oxygens. They don't exist. So we know from that logic that this has to end in ATE. So letter A is out. Where is sulfur on the periodic table? Which group is it in? Sulfur. 16. what kinds of charges do elements in group 16 make? -2. So if the sulfate, well, I just spoiled that. If the sulfate is -2 in charge, that means the cobalt has to be +2 in charge since they're in a 1-to-1 ratio. So cobalt 2 sulfate has to be the correct answer. It can't be +3 because the sulfate's not -3. If it were, we would see more subscripts to balance out those charges. So we know it's an 8 because of the SO4. Sulfate, sulfur with the 8 ending, sulfate is the answer there. The charge comes from our recognition of the ions. And again, there are periodic trends among the polyatomic ions. The oxygen group tends to form -2 ions. The halogen group tends to make -1 ions. The nitrogen group tends to make -3 ions with the exception of nitrates, which are -1. Okay, let's switch gears. Let's talk about acids. Now, acids are easily identified. If we think about hydrogen as having metallic-like properties, acids look like ionic compounds, where we have hydrogen as the cation, and we've got some kind of anionic substance, some sort of non-metal or polyatomic metal ionic associated with it. So our telltale sign for an acid is the recognition of hydrogen at the front of the molecule. If we see something that starts with hydrogen as a compound, then you can bet we're talking about an acid. So that's how we recognize them. How do we name them? We name them based upon the number of elements that are in the acid. If there are 2 elements, we call it a binary acid. Now, binary acids are a little bit tricky because these substances can actually exist outside of water. And when they exist outside of water, they actually are not classified as acids. We would name them as ionic compounds. So if you see something like HCN, HCl, H2S, HBr. Unless it has the designation AQ next to it, we have to assume that it's ionic. That AQ designation, if you remember from chapter 1, indicates that something is aqueous, that's dissolved in water. And so we don't identify it as an acid unless it is dissolved in water. So if you see any of these and they're either gas phase or they are not specifically listed as AQ, then we name them ionically. Hydrogen chloride, hydrogen sulfide, hydrogen bromide. And actually, HCN, which is technically a ternary acid, behaves in that same kind of way as well. CN minus, cyanide ion, has the same IDE ending and behaves kind of like a binary acid does. Hydrogen cyanide gas is extremely toxic and corrosive, When that hydrogen cyanide gas is dissolved in water, it begins to act like an acid. Ternary acids, on the other hand, we have 3 elements usually. It's a hydrogen plus a polyatomic ion. And with the exception of hydrogen cyanide, these only exist in water. So we don't have to worry about, you know, anything funny going on there. If you see H2SO4, HNO3, H2C2O4, H2CO3, all of those are ternary acids. They only exist in water. They don't exist outside of water. We can immediately go into the acid naming system for them. We don't have to worry about what phase they are. And so the 3 elements in play here are hydrogen, the oxygen on the polyatomic ion, and whatever the other element is that gives that polyatomic ion its name. For binary acids, the naming system is pretty simple. We start with the word hydro. We end with the phrase ic acid. And in the middle, we put something recognizable to the element that is attached to the hydrogen. So HCl, hydrochloric acid. The hydro and the ic acid are constant. The chlor is in there to identify chlorine as the other element. For HI, hydroiodic acid. The hydro and the ic acid are constant. The iode is in there to identify the other element as iodine. But again, the key is that aqueous designation. The aqueous designation allows us to go, hey, this is an acid. If I don't have that aqueous designation there, I name it like any other ionic compound. Cation is hydrogen. Anion is chloride in the first case, iodide in the second case. All right. Questions about binary acids? All right, for ternary acids, a relatively simple naming structure as well. Because we're dealing with polyatomic ions involving oxygen, we know that all of those polyatomic ions are either going to end in ATE or ITE. If they end in ATE, we change the name to ic acid. So that sulfate ion that we were looking at in the previous slide, SO4. Sulfate turns into sulfuric acid. So one of the weird things, sulfur and phosphorus, because of that F sound that their ions end with, we do tend to change that up a little bit. Sulf turns into sulfur, sulfuric acid. Phosphorus, phosphoric acid. We, for whatever reason, the FIC sound just does not roll off the tongue very well. And so sulf turns into sulfur, phosp turns into phosphor. If we end in ITE, the name of the acid changes to us acid. So 8 turns into ik, ite turns into us. If there are any prefixes attached, like hypo or per, they just tag along. So perchlorate ion is a good example. It's on your polyatomic ion list. Perchlorate ion, nothing happens to the per. We just change that ending to ic acid. Perchlorate turns to perchloric acid. That's all that we do. So once again, it comes down to recognition. I need to recognize what my polyatomic ions are. And if I can recognize them, if I can name them, then I can pivot by just changing the ending accordingly. We're going to skip the practice here to dive into covalent compounds, covalent nomenclature. Now, covalent nomenclature, what we are looking for here are 2 nonmetals. And the structure is very similar. We had metal, nonmetal, or cation, anion, and ionic compounds. Structure here, first element, prefix plus first element, prefix plus second element, change the ending of the second element to IDE. What are the prefixes? Well, the prefixes are your standard geometric prefixes. One note I will make about mono is that it is only used on the second element. Prefix mono is only applied to the second element. It is never applied to the first element. So if I have one of the first element, I do not put a prefix on it. It's just we name that element. So that's why CO2, for example, we don't call it monocarbon dioxide. It's just carbon dioxide. The mono is assumed if there is no prefix on the first element. All the rest of the prefixes here, again, fall into relatively standard geometric prefixing principles. 3 for tri, 5 for penta, 6 for hexa, 8 for octa, 9 for nona, 10 for deca, and so on. The only ones that are a little bit odd, 2 is di instead of bi. 4 is tetra instead of quadra. 7 is hepta instead of septa. Otherwise, like I said, pretty straightforward from geometry, if you can remember to geometry class in high school. Before we do some practice with this, there are 3 common substances that are molecular, excuse me, are molecular, but are not known by their traditional names. So instead of dihydrogen monoxide for H2O, it has been commonly known forever as water. Instead of nitrogen trihydride for NH3, NH3 has forever been known as ammonia. Instead of dihydrogen dioxide, H2O2 is commonly known as hydrogen peroxide. Those are the 3 that you have to know that are molecular, that are not named by this naming system. In fact, hydrogen peroxide, we can make an argument, hydrogen peroxide is actually known by its ionic system name. O2 2- is the peroxide ion. And if I pair that with 2 H+, I would get an ionic compound, hydrogen peroxide. Let's look at 2 quick examples and then we'll call it a week. Already talked about the first one, CO2. Again, the naming system here, first element, second element, prefix, prefix and suffix. So for C, we would name it as carbon. Since there's only one of them, there's no prefix necessary. For the second one, oxygen, I have to apply a prefix, 2, which would give me di, and I have to change the ending to IDE. So the oxygen gets turned into dioxide because there are 2 oxygens and I have to change that ending to IDE. Put the 2 together, I have carbon dioxide. In the other example, I've got sulfur S and chlorine Cl. For the first one, sulfur, there are 3 of them. Prefix for 3 is tri. So the first element is going to be trisulfur. Tri for the 3 sulfurs. The second element is chlorine. There are 8 of them. Prefix for 8 is octa. Change the ending to IDE, and we would have octachloride. Octa for 8, chlor for the chlorine, IDE because it's the second element, octachloride. I put the 2 together. The name of this compound is trisulfur octachloride. And so the nice thing about molecular compounds is that it's very easy to actually go the other way with them. Because if I know my prefixes well, the prefixes tell me exactly how many I should have. I don't have to worry about charges or anything like that. I just turn the prefix into a subscript based upon what I know the prefix to be. So we now have all 3 of the naming systems all in place. And that's pretty much going to conclude for us chapter 3. When we come back to material on Wednesday of next week, we'll do a couple of examples just to kind of rehash our memory. But we're going to be moving mostly into chapter 4 and talking about chemical compounds and starting to get into some reactions of those compounds starting in chapter 4. I know I went fast. This will be up on YouTube later today if you want to rewatch it and kind of slow things down a little bit. But I wanted to make sure we got through everything so that there weren't any surprises and we didn't have to rehash anything coming back next week. Have a good weekend.